In the Picard's iteration, we have seen that under existence uniqueness theorem, the solutions exist. Now we will look at the proof of uniqueness of the solution. Suppose phi1 and phi2 are two solutions of the initial value problem for first order ODE, namely y dash is equal to f of x comma y with the initial condition y of x naught is equal to y naught. Then we see that both the solutions phi1 and phi2 satisfies the integral equation, namely phi1x is equal to y naught plus integration from x naught to x f of t comma phi1 t dt, and same for phi2, namely phi2x is equal to y naught plus integration x naught to x f of t comma phi2 t dt. So if we take the difference of the two, phi1 and phi2, from the integral equation, we get phi1x minus phi2x is equal to integral x naught to x f of t comma phi1 t minus f of t comma phi2 t dt for all x greater than or equal to x naught. We simply take the modulus. So the modulus of phi1x minus phi2x is less than or equal to integral x naught to x modulus of f of t comma psi1 t minus f of t comma psi2 t dt. Here we know that our f satisfies Lipschitz condition with respect to the second variable. So we have that modulus of f of t comma phi1 t minus f of t comma phi2 t is less than m times modulus of phi1 t minus phi2 t. So we substitute this Lipschitz condition into this given equation. Under the integral sign we substitute this. So what we will get? This is the same equation as above, and we are substituting the Lipschitz condition to the quantity that is there under the integral sign. So we get this is less than integral x naught to x m of modulus of psi1 t minus psi2 t dt. Check here. This quantity came here. Now we call this quantity without this m, namely we call ux is equal to x naught to x modulus of phi1 t minus phi2 t dt. Then what is the condition that we have on u? We note that u of x naught will be integral from x naught to x naught. So u of x naught will be equal to 0. And since this is modulus here, so the integral is also positive. So ux is positive for all x greater than or equal to x naught. Further, since this quantity modulus of phi1 t minus phi2 t is continuous, so this integral is differentiable, and the derivative is the quantity which is present under this integral sign. So we have u dash x is equal to modulus of phi1x minus phi2x, that is this quantity. So this equation 3 that we have, we replace all this thing that we obtained here. So the quantity that is here, you also already recognize that this quantity is u dash x. So u dash x, and here this is m times this integral, but this is m times ux. So you take it on the other side. So we have u dash x minus m times ux is less than or equal to 0. From 3 equation, we have this equation that is at the end of this slide. Equation is u dash x minus m ux is less than or equal to 0. We multiply this equation here by e raised to minus mx. So we get e raised to minus mx times ux dash minus m e raised to minus mx. Ux is less than or equal to 0. for x greater than or equal to 0. Now we can see that this is nothing but derivative of e raised to minus mx ux. So if we differentiate it, first we differentiate on the second term here and leave the first as it is, and the second time we differentiate on the first term and leave the second as it is. So this can be written as derivative of e raised to minus mx ux, and this is less than or equal to 0 for all x greater than or equal to 0. Integrating this from x naught to x, we get e raised to minus mx ux is less than or equal to 0 for all x greater than or equal to 0. And we know that this exponential e raised to minus mx is a positive quantity. So from this we conclude that ux is less than 0 for all x greater than or equal to x naught. But we also know that ux is a positive quantity from this. So ux is a positive quantity, and here we get ux is less than or equal to 0. So the conclusion is that ux is equal to 0 for all x greater than or equal to x naught. So for all x greater than or equal to x naught, ux is constant 0. So for a constant function, the derivative is also 0 over this domain x greater than or equal to x naught. But u dash x is equal to 0 throughout means what? U dash x is this quantity. So this quantity is 0, which means modulus of phi 1x minus phi 2x is 0, which means phi 1 is equal to phi 2. So we conclude that phi 1x is equal to phi 2x. We can do the similar argument for x less than or equal to x naught, and we get the result there also, that phi 1x is equal to phi 2x. So finally phi 1x is equal to phi 2x for the entire domain. So with this we have completed our topic first order ODEs. So we summarize what we have learned here. We know how to solve linear first order ODEs using integrating factor. Then we know Bernoulli equations. They are not linear equations, but they can be reduced to linear first order ODEs, and then we can solve them. Afterwards, we learned how to solve certain nonlinear equations. Namely, if the nonlinear equation is in a separable ODE, that is, it is in variable separable form, then we can solve it. Or equations which are reducible to variable separable form. For example, homogeneous ODEs, they are reducible to variable separable form by certain substitution. Or other equations which can be reduced to variable separable form. Then we learned how to solve exact differential equations. Along with that, we have learned that even if the differential equation is not exact, we can find integrating factor which makes the differential equation exact. Then afterwards, we learned the existence uniqueness results for initial value problem of the type y dash is equal to fxy, where the initial condition is y of x naught is equal to y naught. So here we have the Peano's existence theorem that was proved by Peano, and the existence theorem of Picard. And we know to solve certain differential equations using Picard's iteration method.